Hello everyone. In this lecture we are going to study Fourier transform, in which we are going to see what is the formula for the Fourier transform, and we are going to solve examples on the Fourier transform. Introduction to the Fourier transform. Consider the function f of t, which is the input signal. Suppose it is operated by the Fourier transform, which is also known as the spectrum analyzer. When this input signal is operated by the Fourier transform, then it will give us a function in terms of the frequency, that is f of lambda, which is known as output signal. So basically this Fourier transform transforms function from time domain to frequency domain, where it can be analyzed easily. So consider the example, non-periodic function, which is a single unrepeated pulse. Then when we apply Fourier transform on it, then it will gives us a function in frequency domain, which is known as sinc function. And this sinc function, see, at lambda equal to 0, it will gives us the maximum amplitude. Therefore, in the frequency domain, we can clearly observe that which frequency this signal is carrying, isn't it? And that is very important. So this non-periodic function, it is in time domain. When we apply the Fourier transform to it, it convert it into a frequency domain. Okay, so let us see one more example. Suppose this is the given signal in time domain. We know that any signal is a superposition of sinusoidal oscillations of various frequencies. To analyze or to process any signal, we must know which are the different frequencies present in that signal. Because to process any signal, we must need to pass it through different filters, that is high pass filter, which allows only high frequencies, and low pass filters, which allows only low frequencies. Therefore, to know the nature of different frequencies present in that signal, it is very important. And if we look at to this signal from the time domain, then we cannot draw any conclusion about the nature of the various frequencies in that signal. Therefore, its decomposition is required, and Fourier transform helps in that regard. If we take the Fourier transform of this signal and if we observe the signal from the frequency domain, then it appears like this. This gives us the decomposition of this signal into the various frequencies which is that signal is made up of, and their corresponding amplitude. So from the frequency domain, we can clearly observe which are the different frequencies present in that signal, whether they are high frequencies or low frequencies, that can also be observed, and therefore this Fourier transform is very important. Applications of Fourier transform. Here I have listed only few applications. So first one is in finding solution to the heat equation. So there Fourier transform can be used, or the Fourier integral will be used. Then in image processing, the Fourier transform will be used. Signal processing, as already I discussed, to know what are the frequencies present in that signal so that it can be passed through low pass filter or high pass filter to avoid the low frequencies or high frequencies as per the demand. Then in the theory of communication. So these are the few applications of the Fourier transform. There are many. Fourier transform. Now in this we are going to obtain formula for the Fourier transform. Fourier integral representation in the complex form, it is f of x is equal to 1 upon 2 pi integration from minus infinity to infinity e raised to I lambda x integration minus infinity to infinity f of v e raised to minus I lambda v dv d lambda. Now whatever the highlighted term is known as the Fourier transform. So Fourier transform is, it is denoted by f of capital F of lambda. Lambda stands for frequency. So f of lambda is equal to integration from minus infinity to infinity f of v e raised to minus I lambda v dv. And the inverse Fourier transform is given by, so whatever value of this integration we have evaluated, that is f of lambda, replace it in Fourier integral representation. So f of x, it will become now f of x equal to 1 upon 2 pi integration from minus infinity to infinity f of lambda e raised to I lambda x d lambda. So these are the formulae for Fourier transform and inverse Fourier transform. We are going to write down alternate form for the Fourier transform considering the symmetry for this coefficient or the constant term. Okay, so see what are the formulae in the symmetric form. Okay, symmetric form for the Fourier transform, it is f of lambda is equal to, so that 1 upon 2 pi, that coefficient is splitted into two equal parts. So one we have considered with f of lambda. So f of lambda is equal to 1 upon root 2 pi integration from minus infinity to infinity f of v e raised to minus I lambda v dv. And inverse Fourier transform is given by f of x is equal to 1 upon root 2 pi integration from minus infinity to infinity f of lambda e raised to I lambda x d lambda. So these are the formulas for Fourier transform and the inverse Fourier transform. Now we will see its physical interpretation. Inverse Fourier transform f of x, what it gives us. So if you look at to this formula, what we are observing, f of lambda e raised to I lambda x is the Euler. If we use the Euler formula here, then it will give us cos lambda x plus I sin lambda x. So trigonometric terms are there and integration is nothing but the limiting sum. So basically it is summation of the trigonometric terms. Therefore this f of x, what is gives us? It gives us the spectral representation as it is like a superposition of sinusoidal oscillations of all possible frequencies. That already we have seen in the one of the examples. Okay, just we have seen in the beginning. Then Fourier transform f of lambda, what does it gives? So it gives us the spectral density which measures the intensity of f of x in the small frequency interval. So this is the physical interpretation of Fourier transform. Now we will go to solve one example on Fourier transform. Example, find the Fourier transform of f of x equal to e raised to minus mod x. Solution, Fourier transform is given by f of lambda is equal to integration from minus infinity to infinity f of v e raised to minus I lambda v dv. Now we want to obtain f of v. So given function is f of x is equal to e raised to minus mod x. In that replace x by v. Therefore f of v will be equal to e raised to minus of mod v. Replace f of v in this f of lambda, that will gives us f of lambda is equal to integration from minus infinity to infinity e raised to minus mod v e raised to minus I lambda v dv. Now using Euler's formula, we will replace this e raised to minus I lambda v as cos lambda v minus I sin lambda v. Therefore f of lambda, it becomes f of lambda equal to integration from minus infinity to infinity e raised to minus mod v cos lambda v minus I sin lambda v dv. Now this sin lambda v is an odd function, e raised to minus mod v is an even function. So product of these two functions is an odd function, and hence in the interval minus infinity to infinity, value of the second integral will be 0, and hence we left with f of lambda equal to integration from minus infinity to infinity e raised to minus of mod v cos lambda v dv. Now e raised to minus mod v and cos both are even functions, so is their product. Hence, we can write down f of lambda as f of lambda equal to 2 times integration from 0 to infinity e raised to minus mod v cos lambda v dv. Now, as our interval values are from 0 to infinity, that is they are only positive values, so mod v is equal to v in the positive interval. Therefore f of lambda it becomes now 2 times integration from 0 to infinity e raised to minus v cos lambda v dv. Now we will simplify it further using the formula. To solve the integral, we will use the formula integration e raised to x cos bx dx is equal to e raised to x divided by 1 plus lambda square into a cos bx plus b sin bx. So therefore, integration will be f of lambda is equal to 2 times e raised to minus v divided by 1 plus lambda square, because a is minus 1 and b is lambda. So replace the values and x is v. So replace the values. So integration will be e raised to minus v divided by 1 plus lambda square into bracket minus cos lambda v plus lambda sin lambda v. Limits are from 0 to infinity. Now put upper limit and lower limit, that will give us 2 times. When we put v equal to infinity, then e raised to minus infinity is 0, and at lower limit it will be e raised to 0 is 1, so 1 upon 1 plus lambda square, cos 0 is 1, so minus 1 plus sin 0 is 0, so 0. Simplified, we will be getting f of lambda as 2 divided by 1 plus lambda square, which is the required Fourier transform. I hope you understood this. Thanks for watching this video.